Hi, I'm Corbin Graham from CSC 466, and the paper that I'm going to be presenting is Edge Caching and Computing in 5G for Mobile AR, VR, and Tactile Internet. This paper, by 4 University of Ottawa members, was reviewed and released in the January edition of IEEE Multimedia. I chose this topic and paper due to my own interest into VR developments. The possibility of computing VR assets and applications off-site can open doors to users without suitable hardware to enter the space. This paper does a very good job of introducing many of the fields that can see benefit from future research into this problem. The paper itself actually attempts to tackle more than one problem at once: VR and AR off-site computation and tactile internet off-site computation. Both of the issues, however, suffer from the same central issues: a lack of on-site computational resources, and a consistent ultra-low latency network connection. Before we address the issues themselves, let's take a look at what edge computing, edge caching, and tactile internet actually are. Let's start with edge computing. Edge computing is a new computing technique with the central idea of bringing cloud computation closer to its destination. A current major issue with attempting to do cloud computation of VR and AR applications, as well as tactile internet, is that under normal circumstances, the latency between the user and the server is too high. This often leads to applications' experiences feeling unnatural. Edge computing greatly reduces latency in 2 ways. The first way latency is reduced is by computing the real-time data from the user at edge nodes, rather than all at the cloud central server. Latency is reduced greatly by decreasing the distance between user and computational node. The second way latency is reduced is by distributing computations between several nodes rather than a single node. By doing this, not only can computations be completed more quickly, but the network itself is not hindered by large amounts of data coming from a single network path. A good definition for what edge computation is comes from Karim Arabi, who, during a presentation at an MIT seminar in 2015, stated that cloud computing operates on big data, while edge computing operates on instant data. That is, real-time data generated by sensors or users. As a quick illustration, let's step through this diagram. The bottom of this diagram gives us our users, or in our case, VR, AR, or tactile internet applications. Basic computations may be computed at this level. One level up gives us our edge nodes. This is where the bulk of difficult computations would be completed. Finally, at the top level, we have the cloud. This would mainly be used for storage and fetching of rudimentary data. With this understanding of edge computing, let's move on to edge caching. Edge caching is an extension of edge computing. Utilizing the same edge nodes from computation, they can cache content that is accessed frequently. By doing this, content can be delivered to the user far faster, as it prevents the user from needing to access the cloud. An example from the paper suggests that edge caches may contain recent sporting event videos or newly trending viral videos. Any content that the edge deems as frequently accessed can be stored in this location. Our final definition to look at is tactile internet. Tactile internet is the idea of using haptics as a way of simulating physical touch. Haptics are often closely coupled with VR and AR, as virtual environments currently lack the physical sensation that gives full depth to these experiences. Tactile Internet's goal is to provide these haptic sensations in real time, allowing users to fully interact with virtual environments. A large issue with Tactile Internet, as well as AR and VR, is that it relies on haptics responding at a rate quick enough to feel natural to a human's perception. As a note, all of the above technologies have a reliance on the upcoming 5G network, currently being installed and rolled out. The new 5G network, still being tested and experimented on, has tested speeds capping at 1.8 gigabits per second, with expectations in the future of speeds reaching 100 gigabits per second. A more important aspect is the latency of 5G networks, which currently ranges between 1 and 30 milliseconds. We'll discuss the importance of this latency in later sections. Now that we have all the basic definitions out of the way, let's relay them back to the principles of our paper. The paper can be simplified as an amalgamation of all the current research into the field of off-site computation of VR, AR, and tactile internet applications. Let's take a quick look at why off-site computation is necessary. Currently, virtual reality and augmented reality headsets are prohibitively expensive for a large number of people. An HTC Vive, for example, currently costs upwards of $1,000 Canadian, with cheaper headsets ranging between $400 and $600. Not only are the headsets expensive, but the computational power required to render a full immersion scene at 90 plus frames per second requires a rather intensive computer. If a portion of this computation could be offloaded to other locations, VR and AR become more accessible. An even better alternative for users to enter this space would be if they could leverage a device that they already own. According to Pew Research, mobile phones, and more specifically smartphones, are now owned by over 81% of the United States population. These smartphones are capable of displaying VR content thanks to the help of virtual reality headsets such as the Google Daydream. However, a large restriction is that these smartphones are only capable of either displaying 3D videos or very basic virtual reality scenes. Due to this restriction, multiplayer experiences, as well as detailed virtual reality scenes, are not possible. By introducing a way to complete portions of computation outside of the device, the usability of virtual reality increases dramatically. Now, let's look at how the paper intends to apply cloud computing and cloud caching to VR, AR, and tactile internet applications. The paper's recommendation for how edge caching can help solve computational problems comes in multiple parts. The first part is what needs to be cached. The paper recommends that background scenes of the most popular applications should be cached. The paper also recommends that some form of a chunking algorithm will be necessary to distribute the background content to multiple edge nodes. This moves us into our next point. The paper recommends that, rather than place an entire background onto a single node, that it instead chunk the scene and distribute the content to several edge nodes. By distributing the content, parallel requests can be made to all of the nodes containing chunks, thereby reducing the size of data required to be sent down each network path. Furthermore, as the distribution reaches full saturation for a particular cluster of edge nodes, it may be more efficient to start caching chunks onto user devices. The paper refers to caching and distributing content from a user device as device-to-device communication. All of these combined solutions must, as described in the paper, retain an end-to-end latency of less than 30 milliseconds, as this is what is expected of an online VR game. Now let's look at edge caching for tactile internet. Unfortunately, due to human perception, the required maximum delay for haptics is only 1 millisecond. This is the absolute minimum latency achieved with 5G networks, and is currently only replicatable in lab settings. Additionally, haptics rely on real-time interaction, where it is impossible to cache any information about the scene. With this knowledge, edge caching is not a viable solution for a majority of tactile internet application cases. The paper does, however, mention that caching of haptics may be beneficial in cases where haptic content is only replayed to the user. That is, a series of haptic sensations can be cached and played back to a user. The paper mentions that this may be useful for specific training cases. For edge computing VR and AR applications, the paper cites 3 individual studies. The first, by Czartoryski, utilizes 2 modes of computation in order to achieve an edge computed scene: mech computation mode and local computation mode. In mech computation mode, the user will request a task to be computed at the edge, and the edge will return the result. In local computation mode, the edge, from its cache, will send contents and tasks not stored on the local device. The computation of these contents then takes place at the user's device. A combination of these 2 computation modes aim to minimize communication and satisfy delay constraints. A second study, from Elbambi, suggests a proactive caching strategy in order to satisfy delay constraints. By pre-computing the expected next few video frames on the edge and caching them, the user needs to simply request the next frames from the cache. This minimizes the latency to an acceptable level for VR gaming, as is the focus of this particular study. The final study, from Zhang, places its focus not just onto VR gaming, but onto massively multiplayer VR games. The paper, much the same as the study from Czartoryski, employs a hybrid of edge computation modes in order to rapidly update view change renderings at an acceptable rate. We will now look at edge computing for tactile internet. Once again, tactile internet is likely unachievable with current network and 5G network capabilities. The paper suggests that some form of interpolation of human movement would be necessary in order to achieve both the rapid computation of tactile internet and the low latency of 1 millisecond. The paper goes on to mention a study from Tactile that proposes a multi-leveled edge-based computing system. For simplicity, we will not cover this work in detail. Now that we have reviewed the options laid out for us by the paper, let's do a quick review. A table provided by the paper gives us a quick synopsis of what we've covered. Czartoryski's paper, offering the two-mode computation strategy, was evaluated for throughput, caching capacity, and energy consumption. Albumbi's paper, for proactive caching, was evaluated for network delay, throughput, and computing capacity. Zhang's method of hybrid computing for massive multiplayer VR games was evaluated for network delay and computing capacity. And the final study that we reviewed, from Tactile, which proposed the multi-leveled edge computing, was evaluated for network delay and response time. It is clear from this chart alone that future research is required in order for us to satisfy more or all of the constraints. After addressing both edge computing and edge caching, the paper continues on to mention areas of interest for this research. In the interest of time, I will only quickly review each. Edge computing and caching can, as already mentioned, be applied to the entertainment world, more specifically VR games. Edge computing and edge caching are very promising for this field, as current cloud computing can already almost solve this problem. Next, education. Education will likely benefit more from tactile internet, as it may be used for remote surgeries or to participate in lab experiments. As mentioned in the paper, it is less important for these features to be implemented on a mobile basis, as it is likely that the user would not be mobile for education purposes. Art and culture is also a driving field, especially for AR applications. As in the paper, AR can be used to enhance user experiences at a museum by augmenting information over top of art installations. Another mentioned attribute would be for large AR art installments that allow users to interact with each other and AR objects. Healthcare, similar to in education, can benefit by allowing for remote surgeries. This is most important when a specialized surgery, one which very few surgeons know how to perform, needs to be completed. Allowing the surgeon to complete these operations remotely gives them more time for other surgeries. Additionally, tactile internet can be used for physical therapy purposes. Finally, intelligent transportation and autonomous vehicles can benefit by being able to interact with one another. Training of these vehicles may be possible by creating VR spaces for the cars to train on. For the final section of this paper, we look at the challenges and open issues that plague edge caching and computing. First is cache size, cache management, and computing costs. Further study is needed into what to cache, how to cache the files, and the size of a cache required to store all of the required data. The next issue is the quality of experience model. Currently, quality of experience and quality of service are distinct and separate measures. Given the demanding requirements of VR, AR, and tactile internet, these concepts will need to be combined. Meaning, degradation of the quality of service will almost always mean degradation in the quality of experience, and vice versa. Fairness in offloading is an issue where, based on the computational power of a user's device, it may attempt to access the edge more frequently than other users. This can lead to an unfair advantage given to higher computation devices. This may leave lower computation devices starving for edge resources. Again, further study is needed in this area. Another presented issue is a correlated content model, such that if multiple users are viewing the same 3D video soccer game at the same time, it will likely be possible to deliver the content utilizing a single computation for multiple users. A very important issue is that this paper focuses exclusively on homogeneous users who all have the same computational power. In the real world, there are many different virtual reality devices, each with their own set of strengths, weaknesses, and available computational power. Edge computing and caching based on a user's capabilities is an open issue. A final issue is user privacy and security. This is especially important in the case of device-to-device communication. Now that we have made it through, let's do a final review of the paper's contents. From this paper, we can get some insight into the current research taking place in the field of VR, AR, and tactile internet research. The paper presents to us solution models for VR, AR, and tactile internet with the utilization of edge computing and edge caching resources. The paper does a great job of acting as a springboard for future research by combining much of the relevant research for edge caching and computing of VR. Finally, the paper brings together all of the recommended areas of future research, driving other researchers to fill these voids. Thank you for watching.